Hey mathletes, we're checking out the second part of our trig double unit. We're looking more at the application this time, and we're starting off with 11C, which is trig identities. We can talk about them as relationships between trig functions. So sometimes we use these identities they're sort of like rules or shortcuts to simplify expressions, simplify equations. So often you'll see this concept that tangent is sine over cosine, and that's because the sine is the y value, the cosine is the x value. So if you're looking at the tangent of an angle, it's really tangent is opposite over adjacent, and opposite is sine and adjacent is cosine. So that's where this piece comes from. That's a trig identity. It holds true for all trigonometric functions, and so we can use that to mess with equations. We can also surmise this idea that sine squared plus cosine squared is theta. What this really means is sine of theta squared plus cosine of theta squared equals 1. We just write this in a shorthand with the squared here, so it's not confusing if the theta is squared or the whole thing is squared. It means the whole thing is squared. Where this comes from is this. We know in a unit circle the hypotenuse is 1. Oh, that's an awful line. The hypotenuse is 1, equally awful. And we get that from right triangle trig, which you get a squared plus b squared equals c squared. One of the sides is sine, one of the sides is cosine, and if you think about this as a squared plus b squared equals c squared, Pythagorean theorem, we know that the hypotenuse is 1, so that's where this comes from. We also know that one side is cosine, the other side is sine, so that's where these squared terms come from. Okay, so those are the two big identities that we'll see the most of right now, and it comes from the unit circle. A repercussion of this is that you can make expressions that are equal to just sine squared or just cosine squared if you subtract the other one off. So if you subtract cosine squared from both sides, you end up with sine squared is 1 minus cosine or squared, or vice versa, subtract, and you get cosine squared of theta is 1 minus sine squared of theta, and you use these often as well. So these are nothing more than Pythagorean theorem applied to the unit circle. Okay, let's try those out in a second. One other piece is that you can treat cosine theta just like an x or a y, right? You could think about this as like 3x plus 4x, right? How many x's? Well, 7 x's. But instead of x, it's cosine of theta. So this is really 7 cosine of thetas, right? You can treat them like equations by themselves. So let's try this out. I want to simplify these two. You can either follow along with me or pause me and see if you can do it on your own. I can see that there's 2's in both of these, so let's factor out a 2. If you factor out a 2, you're left with 1 here, and you're left with just sine squared theta. This is, where did it go? Where did it go? This is cosine squared theta, because we know that sine squared theta equals plus cosine squared theta equals 1, right? And we'd solve for sine squared theta we'd solve for cosine squared theta, and we'd put this in instead. So we're just trying to simplify and make it as nice as possible. So you would use the follow-up equation from this and say this is really 1 minus sine squared theta. Replace that, and there you go, simplified. As nice as we can get it. This piece, you can do the same thing. This looks awful, but they both have signs. This is cosine theta times cosine of theta times sine of theta, and this is sine of theta times sine of theta times sine of theta. Pull out a sine of theta, right? And you end up with this, right? Factor out a sine of theta. You're left with just the cosine squared. Here you're left with just sine squared, and that is 1. Ping, right? So you end up with this, just sine theta. Neat. All right, let's try another one out. When you first attack this, I really want to take the 2 out. You get 1 minus cosine squared theta, and over 1 plus cosine of theta. I'd like you to use cosine and not cos sine and not sin, and tangent instead of tan. It makes you sound professional. I really want to turn this into sine squared theta over 1 plus cosine of theta. But now we're kind of at an impasse. Like, I can't really clean this up anymore. If this was 1 minus cosine squared, but we're not making this any simpler. So I'm going to backtrack and do this. Instead of rushing into it and trying to flip this sine squared theta, I might think of this as 1 minus x squared. And if you think about it as 1 minus x squared, this really is the difference of two squares. You could think of this as 1 minus x and 1 plus x, right? The 1's give you the 1, the negative x and positive x give you the negative x squared, and 1x minus an x gives you no middle term. If we play this same game with cosine, we can turn this piece into 1 minus regular cosine times 1 plus cosine, all over 1 plus cosine theta. And lo and behold, your 1 plus cosines cancel out, which is lovely. This whole thing cancels out, and you're just left with 2 times 1 minus cosine theta. Maybe throw this back in, maybe not. Let's see what they did. Hopefully, there's that. Yeah, there's that. Yeah, they left it. Cool. Another sneaky way to do it. All right. All right, and so for the last piece, let's just try to expand this and simplify. So cosine theta minus sine theta, do not make the mistake of dropping this in, right? That doesn't work. Think about like 2 plus 3 squared. If you this should be 5 squared, this should be 25. If you drop the 2 in there and there, you get 4 and 9, and that's 13. And we shouldn't get 13, we should get 25. You expand this by foiling, or binomial multiplication, right? And you get 4 and 6 and another 6 and 9, right? And that gives you 25. So that's how you multiply binomials. Do it in the same way here. So expand this to say I've got 2 of these multiplied by each other. If that's hard to see, you could write it out: cosine theta minus sine theta, right? Times itself. There we go. Bah, too big. And when you do your foiling bit, you get cosine squared theta. You get positive sine theta, and you get a cosine sine and a cosine sine. They're both negative. So that's this piece, 2 of those. All right, fine. With your nerd goggles on, you could probably already see this is sine squared theta and cosine squared theta, so put them over by each other. So here's cosine squared theta, sine squared theta, added up. Here's the other bit, and this piece becomes 1. Right? And you're just left with that. So that's this part, and then this is that's the leftovers, and I think that's as nice as we can get it. Sweet. All right, so that's it. Take what you know, take these trig identities and put them in, see if you can change things around and simplify it. One way is not always the best. Like, there's not always one method to do it like this. Sometimes you have to expand it, use your ideas of factoring. You're just solving equations, but with trig buried in there. Cool, good luck.